All right, section 7.7.1 on higher degree polynomials. So we have a bunch of definitions here. First definition is of higher degree polynomial. A polynomial with degree 3 or higher are called higher degree polynomials. A point on the graph that is higher than all other points near it is called a local maximum. A point that is lower than all other points near it is called a local minimum. The end behavior is what happens to f of x as x takes on extreme positive and negative values. In this slide, we see a graph of a cubic function. They give us the function equation right there, y equals 4x cubed minus 120x squared plus 900x. And we're identifying some of the terms that we defined on the previous slide. Let's start over here on the left, sort of at the beginning of the graph. It says down here, as x decreases, y also decreases. So what that means is as x decreases, if you think of the graph as going from right to left, then y is decreasing because that graph is going down. Right? That makes sense. That would be considered one of the end behaviors. So up here, this is a local maximum. This function has a local maximum at the point 5, 2000. Because obviously that point is higher than all the points near it. Go down here. This function has a local minimum at 15, 0. Because that point is obviously lower than all the points near it. And finally, another end behavior. As x increases, so as we read the graph from left to right, we can see that y is also increasing because the graph is going up. So this is another end behavior. The number of real x-intercepts a polynomial has is equal to or less than the degree of the polynomial. So this is actually something that we talked a little bit about prior to this lesson, right? That a quadratic, which is a second degree polynomial, could have up to 2 x-intercepts. A cubic, which is a third degree polynomial, could have up to 3 x-intercepts. If you had a fourth degree polynomial, it could have up to 4 x-intercepts, and so on and so on. So we look at the example once again of our quadratics. So a quadratic could have 0, 1, or 2 real x-intercepts. And I emphasize the word real because we also know that there are complex intercepts as well. So when we look at the diagram here, we have graphs A, B, C, and D. If you look at graph A, which we see right here, we once again see the scenario where that parabola does not cross the x-intercept. So it has no real zeros, no real x-intercepts. But of course it could have complex zeros. In part B, or example B, we see the parabola here that crosses the x-intercept twice. So it has 2 x-intercepts. Part C, here's an example of a quadratic that has 1 x-intercept because it touches the x-axis once. And same with part D, also touching the x-axis one time. So these 4 cases cover the 3 possibilities that a quadratic could have 0, 1, or 2 real x-intercepts. we can apply the same information to a cubic function. These are the three scenarios that we've also already talked about, where a cubic function could have one x-intercept because it crosses the x-axis once. It could have two x-intercepts because it crosses the x-axis twice, or I should say touches the x-axis twice. Or it could have three x-intercepts because it touches the x-axis three times. Alright, in this example, we are being asked to find a polynomial function whose graph has x-intercepts 3, 5, and negative 4, and y-intercept 180. Then we're going to be asked to graph it and describe the features of the graph. Okay, so we just learned that a quadratic function can have at most two x-intercepts. So we know that for this example, it cannot be a quadratic, right? We know a cubic function can have at most three x-intercepts. So this could be a cubic function. However, let's take the case of a fourth degree polynomial. A fourth degree polynomial would have at most four x-intercepts, which means it could also have three x-intercepts. So the best polynomial function for this example, it could possibly be a fourth degree polynomial. But we don't know for sure if that would apply here. So whenever we have a problem like this, what we do is we take the type of polynomial with sort of the maximum x-intercepts. So if they're telling us that this polynomial function has three x-intercepts, we know that the smallest degree polynomial that would have three x-intercepts is a cubic function. So that's what we're going to use. So we're going to start out our cubic function by writing the factored form of a cubic. We've done a lot with this factored form. We know that R1, R2, R3 are the x-intercepts, and that A is the vertical dilation. Now the example is telling us that the x-intercepts are at 3, 5, and negative 4. So we're going to plug those in for R1, R2, R3. X minus 3, x minus 5, x minus negative 4 would be x plus 4. Since the y-intercept is 180, we know the x value of any y-intercept is 0. So this will allow us to solve for a. So we plug in 180 for y. We plug in 0 for all the x's, so we have negative 3, negative 5, positive 4. Simplify. Negative 3 times negative 5 is 15. 15 times 4 is 60. So we have 60a. Divide both sides by 60 to get a by itself. A is going to equal 3. So we can finish up by writing our polynomial function as the function y equals 3 times x minus 3 times x minus 5 times x plus 4. And that's our final polynomial function written in factored form. So the next part of the problem says to graph this function and then describe the graph. So we pull up our calculator, hit y equals, we're going to plug in 3 times x minus 3 times x minus 5 times x plus 4. And again, we're going to have to apply an appropriate window. We're not quite sure what this graph is going to look like. It's always a good bet to start with the standard 10 by 10 window. Ooh, wow, okay. So you can kind of picture this graph. It's going to have the shape it went up and then down and then back up. But obviously we can't see the top and we can't see the bottom, so we're going to have to change the window. Alright, so let's go to window. Let's increase our maximum y and decrease our minimum y. I'm not quite sure how much we're going to have to do this. Let's start out negative 20. Oh, excuse me, that's the x, so we don't want to change that. That looks funny. So down to y. Negative 20 to 20. Right. Alright, looks like we're going to need some more. So let's go back to window again. Let's go down to the y. Let's go negative 30 to 30. And let's now count by 2s. And it's going to be important that we remember that we're now counting by 2s on the y. Okay, we can see that local min, but we can't see the local max yet. So let's increase our maximum y. Looks like we have to go significantly bigger than this. Let's go 60 and see what happens. Graph. Still got to go bigger. Window. Let's go 100 and see what happens. Ooh, it's way up there. Okay. Window. Let's go 150. We're getting there. Window. 200. We're almost there. Let's go 220. And let's count by 10s now. Oh, okay. There, we can see the whole graph now. And again, we talked about how getting that appropriate window is a skill in of itself. And, a lot of trial and error just based on seeing the graph. Okay, so now we're being asked to describe this graph. So we start with the end behavior on the left part of that graph. As x is decreasing, y is decreasing. That's the far left part of the graph over here that you see at the bottom. There's a local maximum. Let's find this local maximum. Trace, and it's going to be somewhere up here. But let's actually find it. I'm going to show you how to find this. Let's do second trace, and we're going to calculate number 4, this maximum. So hit enter. It's going to ask us for a left bound, so we have to go to the left of that local maximum. It's going to ask us for a right bound, so we have to go over to the right of that. And then it's going to ask us for a guess. And it's somewhere up there. Our local maximum is right there, negative 1.395118, and the y is 219.64859. And then we know, of course, that there's going to be a local minimum way down here, right? So trace down again, it's way down here. Well, let's calculate that local minimum. So again, go second, calculate, and let's calculate number 3, the minimum. So left bound, we're already on the left side of that local minimum. Right bound, we need to go over here, come up the other side. Oh, that's a little bit too far. There, and then guess. And the guess doesn't even have to be accurate, it just needs to be between the two bounds. There it is, 4.06, comma, negative 2.4, or 24.09, it looks like. Okay, so that shows you how to find those local maximums and minimums with the calculator. And then finally, the end behavior over here on the right is that as x is increasing, y is also increasing. So that describes that graph pretty thoroughly.